Imagine having enough funds, enough volunteers, and tons of data, and still not being able to help the people who actually need it the most. That's the reality many NGOs face today. The problem isn't a lack of resources, it's scattered and inconsistent data. Data is stored across multiple places, leading to redundancy and conflicting information. And since there is no centralized system to analyze everything together, decisions often go wrong. So what happens is some areas get more help than they need, while others are completely ignored. And overall, the resource allocation becomes inefficient. So we built JanSeva, a centralized platform where NGOs can upload their survey data, which is then cleaned, structured, and stored properly. This allows the system to analyze needs across regions and match volunteers and resources with the actual demand. In short, clean data, smart allocation, and better impact. Now, briefly, how our system works. We start by collecting data from multiple NGOs and survey sources. Then we clean and transform it using ETL processes, removing duplicates and standardizing formats so the data becomes consistent and reliable. This clean data is then stored in a structured database, optimized for efficient storage and fast retrieval. On top of that, using query-based analysis, we built a smart ML-driven pipeline that analyzes regional needs and intelligently matches volunteers and resources with the actual demand. Coming to the tech stack, on the front end, we use React with white and tailwind CSS to build a fast, responsive, and component-based interface. This allows dynamic rendering and smooth user interaction. On the back end, we use Node.js with Express to handle API requests and core logic. And for the database, we use MongoDB, which gives us the flexibility to manage dynamic NGO and server data efficiently.
Now, let's look at a core feature, how volunteer connect with NGO through our approval-based join system. We built this to ensure NGO maintain full control over their workforce. Here is the volunteer NGO controller. When a volunteer apply, they hit request to join NGO endpoint. Here is the request to join NGO hit point. This doesn't add them instantly. Instead, it creates a relational record with a pending status. NGO can view this pending request on their dashboard. When they accept a volunteer, they trigger approved request endpoint. Here is our approved request endpoint. Notice how we perform a backend check to ensure NGO approving the request is actually authorized owner. Once verified, the status updates to approved and NGO's volunteer count is dynamically incremented. Let's look at the core backend infrastructure of JanSeva, starting with our secure authentication and role management system. To ensure authentic user, we have implemented an OTP-based email verification system. As you can see here in our auth controller, when a user sign up, we verify their OTP before creating their account and also generating a secure JWT token. During this process, we also handle dynamic role assignment. Looking at our user module, users are strictly categorized into roles like admin, NGO, and volunteer. This is critical because our entire applications rely on our custom authorization middleware. Here is our custom authorization middleware. By passing required roles into authorized functions, we securely lock down our routes. This guarantees that NGO can't access admin controls and volunteer can't access NGO specific data.
Briefly explain our database design, key schema decisions, and a live query flow from front-end to MongoDB and back. So here we use the MongoDB. So our database is a collection of collections. So we use MongoDB as our primary database, and around 11 core collections are used, like users, NGOs, campaigns, contributions, service requests, volunteers, villages, and reports, and many more. Although the MongoDB is a NoSQL database, but we designed it using a relational approach for better structure and consistency. So we use ODM model, object data modeling, object ID based references such as user ID, NGO IDs, which behave similar to the foreign keys in the relational database. For the performance thing, we use different optimization techniques like indexing, the compound indexes for efficient filtering, and the 2D sphere indexes for the geospatial queries, and the text indexes for the search functionality. We also carefully balance the referencing and embeddings. A hybrid mode is used, using the reference for the relationship and embedding computed data like scores to reduce joins for the better performance. So let me demonstrate you a query flow. When I select filters like state and category and run query on that page, the front-end part, the React sends an API request with the query parameters by building a URL, and the backend Express receives the request and routes it to the controller. After that, the query execution process takes place. The controller builds a MongoDB aggregation pipeline where different keywords are built in the pipeline. Like example, the $match is used, the $group, the $lookup. Like $match is used for the SQL query, SQL where query. We also used different keywords to execute multiple aggregation pipeline in parallel. For the optimization purpose, the MongoDB query optimizer automatically select the most efficient index for execution. After the backend call, the MongoDB receives the aggregation pipeline call and return the output back to the backend. After that, the response process data is returned as JSON format and rendered dynamically on the front end. So overall, our system combines the relational design principles and efficient indexing aggregation pipelines to ensure both the data integrity and high performance in the real world.
The ML system has four components. First, a random forest regressor built with scikit-learn. It analyzes 40 plus server variables and outputs future importances, telling us how much each variable contributes to a village's vulnerability. Those weights feed into our vulnerability scoring model. A weighted sum that the Node.js backend applies in real time to new survey data. No need to rerun the full ML pipeline. For volunteer deployment, smart matching uses capacity aware around robin, scoring each volunteer on their hours, rank, and skill match to find the best fit. And geospatial search uses hours and distance, mapped to MongoDB's near operator to find volunteers physically closest to each village. Server.js. Now let's see how this connects to the database. At server board, one shared MongoDB connection is established. Everything builds on top of that. The ML controller uses it with this single line, no separate connection. It gets a raw MongoDB handle to query any collection directly. The pipeline is pure JavaScript logic. The controller executes it, and this met state writes the computed village scores back to the database, all in one operation.
Now I'm going to quickly demonstrate the ML part of this project. First, I'll log into the dashboard using an NGO email and password. As you can see, there are the pending requests displayed and all the volunteers that are registered to this NGO. And I have the option to download templates for the different kinds of surveys that we offer. And for now, I have an already surveyed sample data, which I'm going to use to create a campaign. After filling all the details, I click on create campaign, and now the ML part is calculating all the vulnerabilities for all the villages. That's why it's going to take a few seconds. Now that the campaign has been created, I can click on the campaign card to get more details. As you can see, there are all the vulnerability scores calculated, and the same is being displayed in the ML hub. But as you can notice, the number of volunteers are still 0 because the campaign has been just created and no volunteers have been registered. So to demonstrate the smart matching pipeline, I'm going to go to an already generated campaign with a few volunteers registered. As you can see in this, there are 1 or 2 volunteers registered. If I go to the smart match pipeline and select the number of villages to be 3 and hit enter, it's going to smartly allocate the volunteers into different groups for each village based on the vulnerabilities of each village. As you can see, there is a wide range of volunteer experiences and their rankings. This ensures that no village is getting over-resourced or under-resourced. The human resources are being split equally and the NGO can work efficiently. The ML pipeline is being called by the backend controllers, which in turn calls the controller in the ML folder of the project, which finally calls the build smart match pipeline in the pipelines folder. The ML pipeline is coded in such a way that it leverages the aggregation pipelines in MongoDB and writes sufficient queries for faster data access. As you can see, first we match if the volunteer is available or not, then we look up for the volunteer score using another query, and we check for overlapping skills and domain alignments, and then finally we calculate the geo proximity score and calculate the final match score. Based on this, we format the output into clean readable format, and then we classify the volunteers into different tiers. This is how we can mix smart ML algorithms with efficient query languages for a smoother communication between the database and ML.
Now let me explain about the deployment part of our project. We followed a classic 3-tier architecture wherein the frontend is deployed on Vercel using React. The backend API is deployed on Amazon Web Services EC2 using Node.js and Express. The database is hosted on MongoDB Atlas and managed as the MongoDB service. Now let's start with database. We are using MongoDB Atlas, a fully managed cloud database. Our cluster is hosted on AWS in North Virginia region. Our database is stored in cluster 0. As you can see here, the name of our database is JanSeva, and inside that we can find all the collections that we used for our project. Let me inspect users collection. You can see all the fields that we used in this users collections, name, email, etc. Similarly, all other collections are stored in this manner. Atlas handles replication, backups, and scaling for us so that we don't have to manage any of that ourselves. Next up is our backend. We have a Node.js Express server running on AWS EC2 instance. this one here, it's live at port 5000 on this public IP. Finally, the front end, our React app is deployed on Vercel. Every push to the main triggers an automatic deployment. You can see the build history here. Okay, then we have configured API reroutes to Vercel.json. So any request to /API/ from the front end gets transparently proxied to our EC2 backend. This keeps everything under one clean domain. So, and here's the live application: front end on Vercel, backend on EC2, database on MongoDB Atlas. The front end, backend, and database work independently. So even if we need to improve or update one part, it does not affect the whole system. So, hence making our application more reliable and stable. This is JanSeva. Thank you.